Hello, Algebra 1 students. We are talking about writing and graphing exponential growth functions today. This is section 7.4. So far in Algebra 1, whenever we have graphed a function or graphed an equation, it has created a line, a straight line. It has sometimes had a positive slope, like this one. It sometimes had a negative slope. We've graphed horizontal lines and vertical lines, but all of the lines that we've graphed have made lines. They are called linear. And linear functions are most commonly written in slope-intercept form, y equals mx plus b form. We also talked about standard form a lot of the times, which was ax plus by equals c. And both of these forms, when you graph them, they make straight lines, and we call those linear functions. What we're going to start to do in every chapter from here on out is graph a different type of function, but they're not going to be linear. They're not going to be straight lines. They're going to be something different. And today what we're talking about is exponential growth functions. When you graph an exponential function, specifically an exponential growth function, it doesn't do much for a long time or for a while. And then all of a sudden it takes off. Okay? That's what exponential growth is. Notice it's not a straight line like we used to have where the rate of change is always the same. The rate of change is going to be changing here. Okay? It's not growing very fast, it's not growing fast, and then it all of a sudden takes off. You guys have probably heard of the term exponential growth, or things are going exponential in terminology outside of math class. Okay? With things like going viral. Not too much, and all of a sudden this is this exploding topic of some sort. So it is a terminology used outside of math. Specifically today we're talking about exponential growth, which means that it's going to be growing, it's going to be increasing. We can also have decay, which is going to be going downward. We have these forms, y equals mx plus b and ax plus by equals c for linear functions. For exponential functions, the way that you write them is going to be y equals a times b to the x power. And much like slope-intercept form, where m and b are really important, remember b is the place where it crosses the y-axis, and m is the slope. How much does it rise divided by how much does it run? Right? That's what m and b represent. A and b are going to represent important things as well that you guys are going to be able to discern from the graph. You'll be able to look at the graph and pick out the a and pick out the b. We have a couple of terms before we get started with some examples. First up is going to be just what is an exponential function. An exponential function looks like y equals a times b to the x. We already said that in the last slide. But I'm going to tell you what a and b are here. A is the value of y when x is 0. Okay? A is the y-intercept. That's a critical idea for you guys because you guys are going to be responsible, as the name says, for writing exponential functions. So you guys are going to need to pick out the a and pick out the b and put them in, and then you're done. A is going to be the value of y when x is 0. The b value is going to be the number the output is being multiplied by. So you should be able to look at the table, for example, and figure out what the y values are being multiplied by, and that is the b value. Very easy to write these equations if you guys are given a table. The other terminology that we have, the other vocab term, is exponential growth model. This is a very commonly used model in real life as you talk about investments, or actually exponential functions are going to be used constantly in science classes. But the exponential growth model is going to be the function y equals a. That's a still there. The b value is going to be 1 plus r. And it's not going to be to the x power, it's going to be to the t power, because these are all going to represent real things here. A is going to be the initial amount. Okay, so what do we start with? R is going to be how much it's growing. Okay, in the problem it's going to say, hey, it's growing by 8%. It's growing by 10%. It's growing by 30%, something like that. And that's going to be R. I need you to remember that R needs to be turn into a decimal, because it's always going to be given to you in percents. And you guys need to be able to turn our value into a decimal. And t is going to be the amount of time. Okay, we're going to say, hey, this is growing at this percentage for this amount of time, and it's currently valued at this much money. How much is it going to be worth in 50 years? Something like that. Let's look at some examples. So linear functions are what was talked about in chapters 1 through 6. This would be an example of a linear function, right? Y equals mx plus b. This is the b value. This is the y-intercept. So when x is 0, y is 2. We could plot that if we wanted to. And the slope is 3, which means that between consecutive x values, we are adding 3. Okay, or 0, 2, we could rise 3, 1, 2, 3, run 1, because that's the slope, 3 over 1. But that just gives us also the next point. You'll see 1, 5, 2, 8. We could go to the left 2, -1, -1, and -2, -4, creating a nice line, a linear function. How exponential functions are going to work, I already have the table created. I could not give you this information if I wanted to. What I could do is I could say, hey, plug 0 in for x, plug in 1 for x. If you plug in 1 for x, for example, this is a pretty easy one, you should be able to do 3 to the first power. 3 to the first power is 3, and 3 times 2 is 6. You should be able to create this table doing that. Plugging in 2, 3 to the second power is 9, and 9 times 2 is 18, right? You could create that. I've given it to you right away. When you graph these points, 0, 2 is right here. 1, 6 is up here. 2, 18 would be like somewhere crazy up there. -1, 2/3, and -2, 2/9. If you wanted to, you could turn these into decimals and graph those instead. But that is what this function would look like, exponential growth. It goes this way forever. And actually, if we plotted more points, this line would go towards this axis, but never actually reach it. It's just getting closer and closer, infinitely closer to this axis. And this one's just going to the moon, right? We know it goes up to 18 here. It's like, we can do something like that if we wanted to. Notice, remember, this is a times b to the x power. The a value is what the y value is when x is 0. And the b value is what you're multiplying by every time. 6 times 3 is 18. 2 times 3 is 6. 2/3 times 3 is 2, and we can do this forever. Some problems, it's very hard to see what you're multiplying by. If this was all fractions, it would be really hard to see what you were multiplying by. So in order to get it, you could just take a term and divide it by its previous term. 6 divided by 2. And you could, obviously we know 6 divided by 2 is 3, but if you had just a bunch of decimals or fractions here, you could type it into your calculator. 6 divided by 2, 3. 18 divided by 6, 3. 2 divided by 2/3, you're going to get 3. Let's look at some examples. Write a rule for the function. This should be a very easy task for us. We know that these are going to be exponential first. That's the whole point of this section. Y equals a times b to the x. If we didn't know they were going to be exponential, we would just say, hey, are we multiplying between consecutive terms? And we are. We're multiplying by a constant, right? Between consecutive terms, we're multiplying by the same thing. The number that we're multiplying by between consecutive terms is 2 here, and so that's going to be the b value. The a value is what the y value is when x is 0. So it's 8. And we are done. Y equals 8 times 2 to the x. We could verify this really easily by plugging in 1 and seeing what we get out. If you plug in 1 for x, 2 to the first power is 2, and 2 times 8 is 16. Plug in 2. 2 to the second power is 4, and 4 times 8 is 32, right? This is going to work. We could even do it with a negative number. What's 2 to the negative second power? You guys should know this because we just talked about how to fix negative exponents. you would move it to the denominator and make the exponent positive. 1 over 2 to the positive second power now, which is 1/4. So I plugged in negative 2 for x, and I got 8 times now 1/4, and 8 times 1/4 is 2. So we should be able to reproduce that table if we tried. You guys pause it here, try this one. Should be pretty easy. Remember, it's going to be y equals a times b to the x. A is the value of y when x is 0, and b is whatever you're multiplying by. This was another pretty easy one to see what you're multiplying by, but if you didn't know, you would just do 27 divided by 9, and you get 3. And verify it. Make sure you get the same thing. Do 9 divided by 3. Do 81 divided by 27. Do 243 divided by 81. You're going to get 3 every time. What about graphing these functions? If I told you to graph this one, y equals 1.2 to the x. What I'm going to have you do is I'm going to have you make the t-table just like we just saw. -2, -1, 0, 1, 2. This is going to be your x, of course, and this is going to be your y. And you're just going to plug these values in for x and see what you get out for y. Once you do that, you're just going to plot those points, and you're going to be done. Some of these are really easy, though. 1.2 to the first is just going to be 1.2. You could verify that with your calculator, of course. 1.2 to the 0th, remember from the previous section, anything to the 0th power is just 1. So I've got some of the information right there, but I do need you guys to be able to get the rest of it. This is going to be a lot of calculator work, right? I don't need you to actually show me how you would get this. You can type it into your calculator. You could do 1.2 to the -2nd power and see what you get out. You get 0.69, or you could turn this into a fraction and get 25/36. Now let's do the same thing but plugging in -1. 1.2 to the power of -1 equals 0.83. And then let's do one more. Let's plug in 2. We could do 1.2 to the 2nd power, and that would be 1.44. Then you're going to go and you're going to make your t-table, and you're going to plot these points. 0, 1 would be right here. 1, 1.2 would be there. 2, 1.4. -1, 0.83. And -2.69. So this is hard to tell what it's doing. I might need to plug in some more values. Plug in 3. What do you get out when you plug in 3? I could plug in something like 6 and see what I get out into the equation. I would just need my calculator. 1.2 to the 6th power is 2.98. So 3, 4, 5, 6, 2.98. That would be something like this. So this function is technically growing exponentially. It's just very slow compared to the other ones that we're looking at. Why don't you guys pause it here and try this one? Very similar. Make the t-table. -2, -1, 0, 1, 2. You're going to be using your calculators here, of course. 1 divided by 2, or you could type in 0.5 times 2 to the 0th power. We know that 2 to the 0th power is going to be 1, and 1 times a half is just a half. So I know this one already. It's going to be 1/2. I could do some of these other ones probably too, honestly. 2 to the 1st power is 2, and 2 times a half is 1. 2 to the 2nd power is 4, and 4 times a half is 2, right? So I am able to produce quite a few of these. 2 to the -1st is 1/2. This is going to be 1/4. And 2 to the -2nd is 1/4. This one is going to be 1/8. Now, if you weren't able to do this in your head, a calculator will do just fine. Then you are just going to go ahead and plot these points. 2, 2, 1, 1, 0, a half, negative 1, 1/4, negative 2, 1/8. You can kind of see it taking shape here. Oh, that point isn't supposed to be there, but that's what it's going to look like, right? And we have an exponential growth function. Last problem, we've got a word problem here. Mr. Nyquist has purchased a Morgan dollar. This is what a Morgan dollar looks like. Look how fun that is. That he purchased for $50. Crucial information, I am circling that or squaring it or boxing it or something. He expects the coin to grow at a value of 8%. What will be the value of the coin in 30 years? So remember, from that formula that we had on the first slide, the exponential growth formula is given right there. Y equals A, 1 plus R to the T power. A is your initial amount. In our problem, this coin was originally worth $50, so that's going to be the value of A. R is going to be your rate, and it's going to tell you what the rate is. But remember, you do have to turn the rate into a decimal. Currently, it's in a percent, 8%. Remember, you move the decimal place over twice to turn a percentage into a decimal. So you go 1, 2. 8% is 0.08. So you do 1 plus 0.08. And T is time. This would be 30 years. So let's finish this problem. Y equals, we can actually follow order of operations and simplify inside the parentheses first. We would have 50 times 1.08 to the 30th power. Now, all of your guys' calculators, if you type it in just like this, all of your guys' calculators will be able to handle this. You would type it in like 50, 1.08 to the 30th power. And what we'd come up with is $503.13. So this is how you would use the exponential growth model. Please, if you guys have any questions on any of this, let me know. But that's all I have for you guys for section 7.4.